Okay, so for this problem, so let's read it together. They say the acid dissociation constant of the hydrochloric acid, I'm sorry, hydrocyanic acid. So they are giving you Ka for the acid, and this is equal to 4.9 times 10 to the negative 10. So watch out, they are giving you the acid. Now let's see if you need this one or if you need the Kb. Okay, so they want to know the pH for an aqueous solution of sodium cyanide, and you have the concentration of that sodium cyanide. So when you write it, this is the sodium cyanide, this is aqueous, you put it in water, which is liquid, and what are you getting? Well, so this basically, remember, you can watch this is in a different ways, in a bunch of different ways. You can say that Na becomes a plus aqueous because you're writing the ionic equation for this, and then you have the cyanide, which is the Cn aqueous, right? And with water, right? Basically, remember I asked you write it as HOH. Sometimes helps, sometimes it doesn't really matter. Okay, but when you're forming this, basically you're having the Na plus aqueous NOH because the double displacement doesn't happen because sodium hydroxide is a strong base, so it does dissolve, so sodium doesn't grab on it. And then you have also the H plus okay, so let's write it as basically you have the HCN, though this is still aqueous, and this happens for a small amount, but you have some formation of the acetic or of the hydrocyanic acid, right? So you have this in place. So basically, what you can say, right? Here you can solve, you can put your values there, but basically you can say that your real solution, this is a ratio 1:1 between sodium and cyanide. So they are giving you 0.05 moles of sodium cyanide. So this means you also have, if you're considering also the cyanide anion, this means you also have 0.05 molar solution of this. And you put it in water, right? Again, let's write it as HOH. And then you're going to have, and then you're going to have, so this is liquid. So like we just said, H does take some time to spend with the cyanide, so this is your aqueous, but in doing so, some part of H is taken from the cyanide, while the same amount of OHs instead is released free in the water, right? Because it has lost the partner H. So now your solution is slightly basic. So this is the pure liquid component which you don't care about in calculating your Ka. So now pay attention, you're starting with this 0.05, you have 0 here, you have 0 there, you're losing x. This is what gives you the point of 5 minus x, you're gaining x on both sides, so this is what you have. So question is at this point, are you starting with an acid or you're starting with a base? Since you're starting with a base, you don't need the Ka. What you really need is the Kb, which is equal to Kw over Ka, right? So this is your 1 times 10 to the negative 14 divided by the Ka, which is 4.9 times 10 to the negative 10. And this number is, well, you solve, because I only have 15 minutes of this video. So you solve this one, whatever number you have, remember, allows you to calculate. So this is the number that you have, and the Kb has to be equal to, let's write a small there, Kb is equal to x squared divided by 0.05 minus x, right? Solve for x, and then this, remember, is going to be your POH, which you got to do 14 minus, we'll give you, when you log it, we'll give you the POH. When you minus it from 14, you're going to have your pH, which is what the problem is asking for. And if you do everything right, you should have a, let's see, 11 is your answer. Okay, then next problem. Calculate the pOH for aqueous solution of sodium cyanide. So let's do the copy and paste for this one. So let's go here, and so let's solve this problem here. They want pOH. They are giving you sodium cyanide solution. Which molarity you have? So sodium cyanide has the molarity of 0.0927 moles per liters, right? Molarity. And you have a Kb of 4.9 times 10 to the negative 10. Well, if this is Kb, I think we're good to go, right? Because remember, your ratio is 1 to 1, so this means you have your base, which has a molarity of 0.0927, exactly like before, right? You're adding this to your water, okay, which is forming, this is aqueous, this is liquid, so you're grabbing some H to form this HCN, of which at the beginning you have nothing, and then you're releasing some OHs, of which at the beginning you have nothing, okay? So you're losing X, you're gaining X, gaining X, so this is 0.0927 minus X, this is X and X. Kb is fine, right? And it's 4.9 times 10 to the negative 10, and this is equal to X squared divided by 0.0927 minus X. Again, at the beginning, you can try to disregard the X. If it is a multiple choice and you don't have it, then the only difference is that probably this answer dissolves for more than what you expected, but your this solution is sent to the negative 10, so I think you could disregard this X. So this means that you have a 0.0927 times 4.9 10 to the negative 10, square root this one. So this gives you OHs, okay, an amount of OH concentration equal to 6.74 times 10 to the negative 6, which gives you a pOH of, you just log this name, and it's 5.17. So let's go here. This is what I have, and it's fine. So next one, calculate pH of this also. So copy into the new template here. So calculate the pH of a solution of sodium cyanide. So you have the same problem as before, but listen, you have exactly the same concentration as before, pH, pOH. So how could you change this one into, because right now we have calculated the pOH. How would you calculate the pH instead? So if you do actually, very simply, because you have just calculated the pOH from the problem before, it was 5.17, right? Your pH at this point is just 14 minus the pOH, right? So this one is, when you do this, you have 8.83. So let's go there. It's one of the solutions, so that's good. Submit, and it's fine. Okay, which of the following will act as a weak base in water? So weak base, this is okay. So let's evaluate every single one of those. So none of those, well, it could be, but let's see. Hydroxide, well, hydroxide usually is so what does this do? We take the H, right, to form water. So Cl minus will take the H to increase the OH, but this is a strong acid, will never happen. NHNO3 might grab the H to release the OH, but again, this is a strong acid. ClO minus is not strong because the strong are ClO4, ClO3, Cl, so this one is not strong, so it will take some H, therefore releasing some OHs in water. And the OH, compared to those, I don't think is strong enough to, plus, I mean, if you grab the H, you will just form water. So definitely doesn't belong. So I will go for that answer, and it is right. Next one. One more problem. Determine pH if you have this amount. And so you have pH given, you have to determine the pH. You have this molar solution for the KF. KF is the salt, and when dissolves in water, K is completely released, so now you have the F in place alone, right? So let's do this again. Okay, so you have Ka, but again you have KF. KF would dissolve in such a way that K doesn't belong. So if this one breaks into K plus and F minus, right? And this is the 0.45. The ratio is 1 to 1, so this is also 0.45, but this is K plus, will never attach to the OH because it's a strong base, so we don't care about this one. But this one is the amount we care about. So basically, we can say we start the problem with the anion, of which you know the concentration, which is 0.45 molar solution, right? And this is aqueous. You put it in water, which is a pure liquid, so this means doesn't belong in the reaction. It doesn't change the pH on its own. We just don't consider in the calculation for the K. And this will give you the HF, which stays because this is a weak acid, of which you have nothing at the beginning, and this will release some OH inside the solution. And you have nothing at the beginning. This one loses X, this one gains X gains. So at the equilibrium, you have 0.45 minus X, X, and X. Now, they gave you the Ka. I don't think so because I'm dealing with a base. So Kb is equal to 1 times 10 to the negative 14 divided by 7.0 times 10 to the negative 4. So this will give us 1 times 10 to the negative 14 divided by 7 a negative 4. So this will give us a 1.433 times 10 to the negative 11. Again, the concentration is very small, the constant, so you can disregard this one. So Kb is also equal to X squared divided by 0.45, which gives you a concentration of OH minus. So this is times 0.45 square root, and this is very small, it's 2.54. So 2.54 times 10 to the negative 6, which gives us a POH of 5.60, which means a pH, which is what they are looking for, of 8.40. So this should be our answer. We have it right there. Submit. Correct. And let's stop